Okay, let's start with just a little bit of a transfer from scalar values to their vector parts. Okay, so the scalar values are distance, normally noted as s. In vectors, we talk about displacement. And when we're doing displacement, we normally use a vector r or s. The r is mainly used to talk about the position vector. So that's what a displacement is. They are positions in space, or position vector. When we come to speed, we talk about, distance. In physics, you talk about d, you talk about speed as s. And we talk about vector velocity. And they're normally given as u and v. Sometimes we use w as well. And u is normally the initial of any phase. And what you may see, and you will see me use quite a bit, is subscripts on these. The way I normally do my subscripts is I may do a position vector r for particle A, and if I put a number after it, it's normally referring to the time. So we could be talking about vector u for particle A at time 0. Sometimes you just see the number, sometimes you just see the particle. It depends how many parts there are in the question. Acceleration is also a vector. Now, the mechanics book goes on about forces as well, although we haven't covered forces, so we'll come back to forces later. So acceleration as a vector would be to a movement. Now, we've got a number of equations, and those equations will work as long as we're not talking about squaring the velocities and the displacements. You can make those work, but they're not needed for M1, they're normally done for M2. So on our scalar side, we get an equation S equals ut add on 1/2, S equals the start displacement, which normally isn't shown, plus a velocity times time. The vector equivalent of that would be written something like r equals r0 plus the velocity vector times the time. And note time is a scalar quantity. We have no control. It has no direction. It's always assumed to be moving forward. We can do something similar for v equals u plus at, and then the velocity v is equal to the u vector plus our acceleration times time. So the structure of the equations doesn't change too much. Some simple application questions. Simplest one to start with, let's talk about the displacement questions. So we're talking here about things where people are walking and navigating. So exercise 1, or example 1, dealing with displacement. And the sort of question you're talking about is a person leaves point P, travels some distance north, and then some distance east to a position X, and we've got to work out what the distance is along this side. You'd probably create this quite happily, normally, as long as you know north, south, east and west. You'd probably do this through Pythagoras and trigonometry reasonably straightforwardly. To do it is a vector. We start at P and we create a vector going north, which is our first part of our trip. So that's I'll write as a vector R1 for P, and then you need to check what your vectors are labelled as. So north is J, east is I, so we go east, position 2, and my final resulting vector R, what they call the resultant, so the resultant vector is what happens after as a result of all of the previous vectors. So our resulting vector is describe the journey, so we go from P north, so it's R1, and following that we go to R2 to come across to here, and notice the journey goes from a tail, links to a head, which links to a tail, links to a head, and the result vector joins the remaining start to the end, a tail to a head. So let's put the numbers in. So we got R1 and R2. We can write it in two ways. We can do it as a column. So 0, 2 plus 1, 0 gives me a resulting vector as 1, 2. Or we can do it in terms of I and j. So this is 2j plus I. Normally try and put the vector in the order that they come alphabetically. It just helps read what's happening and stops you from making some mistakes. If we're asked for the distance, so to do the distance is how long is this resulting vector? How far am I between these 2 points? And we know that modulus is done by doing the square root of the x component 1 plus the y component 2, and it means my square answer is the square root of 5. That's perfectly acceptable unless they say particularly as a decimal to some significant figures. Okay, so that's your first example. It's a simple thing. The second one's a bit harder. The second one is about a boat moving. So a boat on a river, and what we have is a river moving down. Assume the banks are parallel. The river moves at a speed of 4 kilometers per hour, and we've got a boat on the side here, and initially we're going to be told that the boat is they'll probably give you it as an angle. They might say something like it's 54 degrees with a speed of 5 kilometers an hour, and then you'd work out your components. So the vertical component and the horizontal component. Vertical component is going to be cosine 5 cos 54 in this case, and the x component is 54 sine, because of the way that angle's been measured to the side. Should work out as being, we've got a vector doing 5 kilometers per hour along there, but it has components 4 and 3. Okay, so we're going to use that. So we've got to create our situation, and we need to decide which way round are we going to label things. So put in a little note for yourself, add to the diagram I and J. Make sure you know which way round you're drawing it. So we've got a velocity for the water. So I'm going to do velocity of the water. So I'm going to subscript that with W. There's no vertical component, no horizontal component, but there's a downward vertical component, or minus 4j, if you prefer algebraic form. The velocity for the velocity on the boat is going to be 3, 4. No, not 4, 3, sorry. Or 4i plus 3j. And the first question is, if this is the situation going on, what happens when the boat sets off? And what we can do is we can say the net velocity is going to be the velocity of the boat normally plus the velocity of the water. So this is actually going to say what's going to happen in reality. So this 3-4 is what it would do if you were sitting in a rubber ring on the boat, on the water. What would the boat seem to do? So the velocity of the boat is 4-3. The velocity on the water is 0 minus 4. So we get a vector 4 minus 1. And if you interpret that, this actually tells you, sorry, this to be 4i plus 3j minus 4j equals 4i minus j. Well, I'm going to print the notes out. I'll try and do these in different colours. So the 4 minus 1, we interpret this solution. So it means the boat will move downriver. So a logical follow-up to this would be, okay, how must the boat steer? To go straight across. So we need to think about our boat. The boat now, so this is another boat in case 2. We don't know what the x and y components are now. So it's xi plus yj. Or x on y in a vector bracket. The river is still the same. So it's equal to minus 4j, or is 0 minus 4. And what we're actually trying to look for, to go straight across, we're looking at the second velocity, final second case. We're looking at that to be in the form of some speed across AI, but no j part. We want it to go straight across. That means it's not moving upriver or downriver. That's a 0j component of a vector a0. So we need to solve this problem, and hopefully we'll see the benefit of using column matrices now. If I write this vector sum out again, we're using the equation v2 equals v boat 2 plus the water still, and it's the same water. Do it algebraically and you get xi plus yj. So let's remove that in a bit. So this actually becomes AI equals xi plus yj minus 4j. Hopefully when we write it out in the bracket form, we've got a0 equals xy plus 0 minus 4. It's quite clear from this that we now know what y must be. It's more clear here than it is by, let's equate j's. No, we haven't got a j, and that's where people often slip up. Equals y minus 4, so leads to y equals 4, and the same thing drops out from this one. This actually leads to the same algebra, and because we now know y is 4, we know also that v B2, its modulus. The speed of the boat hasn't changed, its maximum speed is still 5 kilometers an hour. So that must equal the square root of x squared plus 4 squared. And hopefully you recognise by Pythagoras, you rearrange it. X equals plus or minus 3. And we're going to choose the value x equals plus 3 to say we're going from west to east. The other solution would be a description of moving from east to west, which if we're on the west bank means we're moving into land, or if we're on the east bank, it's the same idea. So if I was to go from left to right, I need to go at an angle such that we've got 3, 4 as the vector, and that will move me in this direction. And the vector minus 3, 4, and that would move me coming back. That's what those two solutions are talking about. So one of them is about it moving this way, and one of them is about moving backwards. And both of them against the flow, and you're now no longer going to be moving up or down, you're going to move straight across. Possibly you might need to find out the angle, and it depends what they want the angle to. If we say angle to the normal of the bank, we're talking about perpendicular, and that would be, here's the bank, there's my vector, it's doing 3 across and 4 up, and we're to be talking about that angle there. This is the normal, and that's likely because this is also the I direction. So the angle to the normal is going to be the arc of my vector B2. An argument of a vector is A tan the y component over the x component. So that normal angle should be put somewhere else. So I need to just calculate that. So 53 degrees, 1 degrees, and that will be 53.1 degrees to the normal, or 90 minus that, which is 46.9 degrees to the bank.